Hey everyone, welcome back to ROS Insights. In today's video, we'll explore how to measure and analyze the motion planning time taken by MoveIt for your custom robotic arm in ROS2. Whether you're tuning your planner or comparing different configurations, this video will help you understand exactly how long MoveIt takes to generate a valid motion plan. Previously, I had done a video on SolidWorks to URDF conversion where I took a custom robotic arm and converted to URDF file using plugin. If you haven't watched, please do watch it, link is in the description. Note that the URDF generated was compatible with ROS and not ROS2, so we have to make certain changes to the script generated by SolidWorks. Note that this is same file structure you should have obtained from SolidWorks to URDF converter. The obtained URDF is being visualized in the URDF web visualizer, the link is in the description, where we could see that we can't move the joint states unless we disable the auto center to ignore joint limits. This is because there are some mistakes in the URDF that we have generated. Now there are two steps to rectify this issue. Either we can go back to SolidWorks and do the correction and rerun the plugin to get proper URDF. If not, you can solve the issue by directly editing the URDF file, which we look at it. Firstly, let's create a workspace called ROS2 underscore tutorial and create a directory called as src within this workspace. Now come out of src and inside the workspace, let's build the workspace and create a package called custom underscore descriptor that has ament underscore cmake as build type and depends on rclpy rclcpp. We can always add dependencies later as per our package. Now copy the meshes and URDF folder from SolidWorks generated folder to our newly generated folder called custom underscore descriptor. If we look at the script generated by SolidWorks, as you can see in the URDF file that there are lower, upper, effort and velocity is set to 0, which prevents us from rotating the joint states. To solve this, we have to set the limits properly. To do that, initially we have to tell that this URDF is xacro file. To do that, we can rename the .urdf to .urdf.xacro file and later paste this line after XML tag. In this way, we can define xacro macro variables without any worries. Define a xacro variables like pi, effort and velocity. So by calling these names, we can get the associated values. Now we are pasting the values directly in place of zero limits mentioned earlier. Coming to gripper part, I have already noted down few limits and I am manually writing it down so that the gripper rotation are within proper limits as physical system. After doing these changes, I am pasting a macro called default transmission, which is very much required for ROS2 controllers in general. This macro takes one argument, the joint name, and automatically creates a transmission block linking that joint to its actuator. The simple transmission plugin represents a basic one-to-one actuator to joint mapping. Using this macro helps avoid repeating code for every joint in the robot, making your URDF cleaner, modular, and easier to maintain. Once done, we need to set default transmission tag to each joint, and I have shown it here. At last, we are defining Mimic Joint plugin for Gazebo so that Gazebo understands that these links are mimic joints and they mimic the gear 01 link. Note that we have already defined mimic joint in the respective links, but these tags are for Gazebo to understand. Also change the package from 5DOF to current name of your package. Here custom underscore description. Once done, we can create a launch file called gazebo.launch.py and paste the following Python script to run our URDF in Gazebo. Note that you need to change the package name to your package name. Here the package name is custom underscore description, and similarly paste the name of your xacro file. Here it is called as 5dof underscore robotic underscore arm dot urdf dot zakro. So basically this launch file calls Gazebo server and client and tries to load or spawn the robot to the Gazebo scene. Remember to provide name of robot mentioned in the xacro in this field. Before we launch, we need to make few changes in the cmakelists.txt and package.xml file as shown. So this way it can include launch, URDF and meshes folder when trying to build. At present we don't have config folder, so please include it and it will be explained later in the video. If using Python package that is rclpy, then init.py file is important, otherwise build will throw an error. This init file tells that there are Python nodes too. In package.xml, we can see that the package also depends on robot underscore state publisher node, joint underscore state publisher, rvis2 and ROS2 launch apart from rclcpp and rclpy. Now come to your terminal, go to the workspace that is ROS2 underscore tutorial and try to build the workspace using --build. You should see that the workspace is properly built. Now you can run the launch file by using the command ROS2 launch custom underscore description gazebo.launch.py. This should load up Gazebo and you should see the robotic arm there. But as you can see that the joints just fall slowly due to gravity. This is because joints are not currently active, and in order to make them active we need to define ROS2 controllers.
Hey, before we write scripts for ROS2 controllers, it is important to know what is ROS2 controllers. In simple terms, a controller in ROS2 is a software interface that connects the commands from the ROS, like the desired the positions or velocities, to the actual hardware or the simulated robot joints. Think of it like the middleman between your brain, that is your ROS2 nodes, and your muscles, those are ROS2 actuators. For example, when MoveIt sends planned trajectory, it doesn't directly move the robot. Instead, it publishes commands to a ROS2 controller, and that controller handles the sending the correct joint positions or efforts to the gazebo or real motors. Now let's create a config file called as custom description config.yaml file under the folder config which we have created earlier, and we will copy the code and paste these code here. So basically here we could see there are two controllers. One is arm controller and we have got gripper controller. The arm controller states that there are these joints which comes under arm controller and there are these joints which comes under gripper controller. In our case, link 1 to link 5 joints comes under arm controller, whereas the gear 1 comes under the gripper controller. And note here that the other gripper links or joints are mimicking gear 1, so it is enough to mention the parent link or parent joint over here. Now these controllers have a type called as joint trajectory controller or joint trajectory, yeah, forward command controller or joint trajectory controller. Basically this means that we can provide joint trajectory or joint angles to the end effector or our arm controller. That's the whole thing. And here the joint state broadcaster reports the position of all the joints from the simulation back to us. So this becomes a closed loop system where we send commands to the joints and we get the information from the joints to us, and this is using joint state broadcaster. And here we have to take it a note that we have here the command interfaces as well as the state interfaces. These command interfaces provides the position as a command to the robot joints, whereas state interfaces gets this position as the command from the simulation or the hardware back to us. So it doesn't always need to be position command interfaces or state interfaces. It can be velocity or acceleration as a command interfaces, whereas for state interfaces it can be even velocity or acceleration. To make sure that the Gazebo understands that we are using ROS2 controllers, we can create a script called as custom underscore description underscore gazebo dot xacro, and inside this script we can mm, copy paste several lines of codes. So basically this part of the code over here tells Gazebo that we are using .yaml file from the config folder. Then we need to make sure that the name of our URDF file over here must match the robot name, and in our case the robot name is custom description and the same name has to be provided here. After that, let's create ROS2 control tags for each link by creating a new script called as custom underscore description underscore ROS2 underscore control dot xacro. And over here we can paste these code here. So basically we are, since we are, in our case we are using Gazebo as a simulator, hence we provide the Gazebo system as our hardware plugin. But if we had iSAC or reality hardware, then the hardware plugin would change respectively. Now looking at each joint names, so joint names like the link 1, the link 2, link 3 respectively, with corresponding the command and state interfaces, the limit has to match. So hence in my URDF, link 1 joint, if we scroll down, link 1 joint has a limit from upper lower minus 90 to plus 90, and over here in the ROS2 tags I have kept it from minus 180 to plus 180, which is totally fine because this encompasses minus 90 to plus 92. So this is totally fine, but don't try to keep it less than 90, minus 90 to plus 90. That way it would throw an error when you try to plan some trajectory from start to goal. So once all these files are included, now let us create a launch file called as controller.launch.py. This controller.launch.py would call these ROS2 controllers, and we can load the ROS2 controllers. That means the controller launch file launches this ROS2 controllers and activates all the joints. It means that the motors are turned on right now. Okay, so you won't be looking at the robot falling down. You would be looking at the robot where the motors has been activated. So that's what we needed. So how do we write this the launch file? So here if you look at the launch file, we have a package name called as custom descriptor. Make sure that your package name matches here. Then we have a URDF. Then we go inside the file.dof roboticarm.urdf.xacro, right? And the one thing that I forgot to mention earlier is that we need to mention the following Gazebo parameters that we have mentioned earlier inside our file.dof roboticam. For example, we have already defined here the xacro and the ROS2 controller, so we need to describe it here too. So how do we do that? We call those packages or xacro files inside this main urdf.xacro file by utilizing the features of our xacro macro variable, and we can include a custom description. This is the name of my package urdf, and this is the name of my gazebo or ROS2 gazebo tags, and these are ROS2 control tags I've already included here. Now coming back to the controllers.launch.py, once we have successfully loaded this urdf.xacro file, we are going to load the robot state publisher and joint state broadcaster, arm spawner controller. Here inside the arm spawner controller, we have to define what controller we are trying to spawn here. Our name of the controller, that if you go back to our YAML file, we could see that the name of the controller is arm controller. So we keep that arm controller here, and for gripper we have gripper controller, and at the end we gonna return, or we gonna run these functions one by one. So now let's test this out. Come to your workspace, then build your workspace. Then after building your workspace, if it becomes successful, then you can source your workspace. Now let's run our gazebo simulator by loading the robot inside there. Okay, there you go. There are few mistakes here which tells that okay, so the main issue was that since I've been copy pasting several stuff from earlier repo to here, so I think I've made a small mistake. The name of the ROS2 controller, it's just ROS2 controller, not ROS2 control test. So I'm showing these errors so that if it comes to you too, you can rectify these errors easily. Yep, we have loaded our gazebo, and you could see that now since we have not launched the controllers.launch.py, all the motors are not in active state. So in order to make sure that everything is in active state, let's go inside ROS2 tutorial, our working directory. Yeah, we are loading now the controller, and if you go back to the gazebo, you could see that the robotic arm has been controlled, or all the joints are in active state. It means that the motors are turned on. Hey everyone, welcome back. This is the third part of our series where we would use the MoveIt setup assistant as a graphical user interface for configuring our robot for use with the MoveIt API. So the MoveIt setup assistant in general is primary function is to generate a SRDF, that is semantic robot description format file for our specific robot, which specifies these additional informations required by the MoveIt, such as the planning groups, end effector, and various kinematic parameters. For instance, the controllers defined within the MoveIt setup assistance has to match the controllers of our ROS2 controllers, because at the end of the day, MoveIt does the trajectory planning, and that trajectory planning coordinates would be sent to the ROS2 controllers, and in turn the ROS2 controllers will move the robot from start to the goal position. So before we start, it is recommended that you first source your workspace, that is you have to be inside the workspace. Then you source your workspace. Once you source the workspace, we gonna run this following command: ROS2 launch MoveIt setup assistant dot launch dot py. That's Python file. Once we run this, we get this assistant GUI. Since we are creating new MoveIt configuration package, we can press create new MoveIt configuration package, and we can browse to the URDF file. So once this URDF file is inside, we can load files, and you could see the robot is being spawned over here, right? So once we got the robot here, then we can go to the next step, that is defining the self collision. So we're going to keep the sampling density in between, not too high, not too less, because if you keep it too high, our CPU gets overloaded with the sampling density, and that's not recommended. So keep it in between somewhere, which is good enough. Then generate collision matrix. So basically what this does is that it searches for the pair of robot links that can safely be disabled with each other. For instance, we have got base link and the shoulder link. We can disable the base link to shoulder link collision, because they are not the part of the motion planning, and you can easily disable them. Now once we have this, we can define the virtual joint, but we don't have to do that, because I have already defined my virtual joint within my DOF, that is within my URDF.xacro file. As you can see here, if we find virtual joint, yeah, virtual joint over here, I've already defined virtual joint, which is bold to the base link, which may not be there in your file. So what you could do is that you can create a link called as a dummy link called as a world link, and that world link would be acting as a parent link, and our child link is our first link. So in our robot, our first link is base link. So we have a parent link called as world link, and we have a child link called as base link, and in between that we keep a joint called as virtual joint. The type is fixed. So once, if you have already defined this virtual joint, there is no need to define the virtual joints here, so we can skip this step and we can go for planning groups. Now we can add the planning group. Let's name the planning group as ARM. So first we're going to keep ARM as a planning group, and we're going to have a kinematic solver for that. So basically you have got several kinematics solver. You could go to the official website of MoveIt Setup Assistant, MoveIt2 Setup Assistant, and you could look at what are these kinematic solver are. For instance, I'm going to select KDL kinematics plugin, and I'm going to keep the resolution and timeout as a default, and there are no kinematic parameters files. And coming to OMPL, let it be none, and I can select any one of that in the later part of the video. I will show you a C++ script where you can select the planner. Now these are joints. We want link 1 to link 5. Those are the components that we are interested in, so we're going to add joints. Now from virtual joint to link 5, everything comes under ARM group. So press this icon, save the button. Now once again add group. Now this time we're going to keep it as gripper. Kinematic solver, let's keep it none. There are no kinematic solver for gripper. The reason behind that is End effector, because the end effector is not made of links attached in a serial chain, therefore the group's kinematic solver should be set to none. And here we gonna add links instead of add joints. Okay, links and accessory 1 to gripper 2, all these comes under gripper. Save this. Now robot pose, we can give robot pose. This is up to you. If you're not interested in giving any robot poses, then it's up to you. You can skip this step and you can go for end effector next step. But let's say we are interested and we're gonna give one pose name called as home pose, and this is this is my home pose. If you look at that, yeah. Okay, we save this. Once again, add pose. This time we're gonna keep it as gripper. Then arm name is gripper, and if you see, this is gripper. The pose name should be close gripper, and I'm gonna close this gripper. Okay, this is close part. Save. Add pose called as open gripper. Okay, this is open. Now we are going to define end effector. Add end effector, and our end effector name is gripper. So you can give any name for the end effector, and our end effector group is gripper, and our parent link is not world link. For end effector, the parent link is link 5, because from link 5 all other end effectors are being defined, so its parent link is link 5. Save this. Passive joints, there are no set of passive joints that needs to be actuated, not actuated in a state, is not expected to be published for these joints. Then we can go for ROS2 control URDF model. This is not important for us because we have already defined ROS2 control tag in our controllers folder in the second part of our video. Please do check it out, go back and you could see this same file that has been defined earlier. Now ROS2 controllers, this is once again we are not interested because we have already defined the ROS2 controllers. The one important one here is MoveIt controllers. Now let's add a controller, and the name of the controller must match the name of our ROS2 controller. For instance, our ROS2 controller name was ARM controller. Let's copy this and paste it here. Follow joint trajectory, this is totally fine. Define and add a planning joint group, and this is the one. Save it. Now add one more controller, and this time the controller name is gripper controller, and same thing, and the recommended added planning group is gripper. Save this. Once it's done, we can go for perception. Since we are not interested in 3D perception or sensors, which I can make one more video on top of these perceptions where you can train some algorithm like 3D machine learning or deep learning algorithms on top of this 3D perception sensors to do some task, which we will look at it later. Then we go for launch files. What are the launch files that we are interested? We can keep these launch files or we can remove these launch files, that's up to you, but let me just keep these launch files as it is. Then later we can delete it if we are not interested in any of that. Now author information, this is the mandatory step. Even if you skip this, the configuration files will never work. So let me keep my name and let me keep my dummy mm, email. Now configuration file, where do you want to save these files? Now let's browse and let's go to here and let's open it here. Custom descriptor. Mm, okay, let's create a package. It's a very simple package with, sorry, it's not a package, rather I would say a directory. Let's create a simple directory because the MoveIt will create CMake list files and stuff like that, so we don't have to make the CMake list or package.xml. MoveIt will do that, so we'll just give a folder name called as custom MoveIt files. Right now we will go back and src, no, we are not interested in src. Move it file and open. Yep, now we are inside the MoveIt file, and these files will get generated there. Now generate package, it tells that no virtual joints has been added. This is totally fine because we have already mentioned the virtual joint in our URDF file. Okay, now let's press OK, and 100% it's generated 100%, right? So we can exit from the MoveIt setup assistant. We can go inside the custom MoveIt file and we can find the config file over here. Yeah, config file, configuration file, and as well as launch file. Now, instead of using the launch file that they have generated, let's create our own launch file. It's called as moveit.launch.py. So inside that launch file, what we could paste here is we can paste this launch file over here. So which basically does is that we are defining our custom description package where we have URDF file inside that. Then inside that we have a xacro file called as fileof robotic.com.xacro, which is right. And yeah, inside this package, that is custom MoveIt file, we are going to find something called as custom description.srdf, which is true. We do have custom description.srdf. We're gonna load MoveIt controllers. Okay, that is also there, and kinematics.yaml file. Now let's look at this config file one by line. uh, yeah, and yeah, we will look at this config file one by one line by line. Since we have already generated ROS2 control.xacro file, so it's not that important here, so we'll skip this part. We'll go to srdf. In the srdf file, as you can see, the group name is arm, and inside that we have generated some joint names, and inside the gripper we have got accessory 1, accessory 2 as a gripper, which comes under the gripper group name. Then we have got home position, which we have defined in the MoveIt setup assistant. Similarly, we have closed state, we have open state. We do have an end effector, which is gripper, and the parent link is link file. And these are the disable collisions, which literally tells that by default it is assumed that any of these links of the robot could be potentially come into collision with any other link in the robot. So this tag disables the collision checking between a specific pair of links. Okay, so it does very good job as in picking up those links which are not required to calculate the collision between each links, right? So that's it does it pretty well. Does that pretty well. Okay, so we have that, and we can go inside the custom description.urdf.xacro file over here, which once again we don't need to do that because we have already defined this xacro file back in our custom description. Now coming to initial position, now this should be floating number instead of int over here. Then joint limits, this sometimes provides you with error. So what you could do, you could mention instead of int we can put it float values. Yeah, once we are done we can go to kinematics plugin, which anyway it's proper. MoveIt controllers. Now this name has to, once again I'm telling this name has to match our custom descriptor config file, which is true because this is controller, arm controller, and we do have here arm controller, right? And we have gripper controller, and the links defined under arm controller matches with our links which are defined inside the ROS2 controllers, right? So this is right now. Then yeah, even good for gripper controller. Now what else we can do? Pills Cartesian limits. These are the limits for the Cartesian XYZ coordinates. So these things are also defined proper. Now we could build the package. We can build the workspace. Now let's try to launch Gazebo, and here was to launch custom underscore controllers, and over here okay, let's run one by one. So first we are launching Gazebo, then we are launching the controllers to activate those joints. So let's verify whether the joints are activated. Yes, it is. Then we can go for moveit.launch.py, which should open up our RVs, and we have our robot over here. So once we have a robot here, we can keep the simulator side by side so that you could see the motion planning happening parallelly. Here, instead of chomp, select OMPL, come back to the planning group, select the planning group as ARM, then select some configuration. Let's say I would like my robot to move in this fashion. Okay, now what we can do, we can go here, plan and execute, and you should see your robot moving in the Gazebo as well as in the ROS2, right? So it's moving right now. Now we could select gripper. Once again, come here, select OMPL, and you can select, yeah, let's close the gripper. As you can see, these accessory 2, accessory 1 and gate 2 is grayed out, which literally means that you cannot move this, you cannot slide here and there because these accessories are mimicking gear 1. So be careful in that. So if you want certain links to move from one lower limit to the upper limit, you should make some changes. You shouldn't make those links to be mimicking other gear. Okay, now come back, plan and execute. Can see your robot. Okay, let's keep it open, plan and execute. Yeah, it's very hard to check. Yeah, okay, this is good. Now we're going to move to the last part of our series, that is how we can generate C++ MoveIt interface script that would talk directly to the MoveIt and generate random poses to calculate the planning time taken by the OMPL. Let's look at that. Hey everyone, this is the final part of our video where we are going to create a ROS2 node that interfaces with MoveIt using C++ and randomly generate robot configurations, measures the planning time using OMPL's RRT Connect planner. You could use any of the planner, but here I'm using RRT Connect, which is tend to be faster compared to any other type of precise as well as faster compared to other type of planner. And after that we gonna execute successful plans. Even if there are some failures in between, we're gonna loop back and we're gonna make it successful until we get it successful each iteration. Then we're gonna iterate for 50 iterations, then log all the planning times to a text file for the later analysis. So in the end we would get a text file that contains the planner's planning time it took to plan a successful iterations. Okay, so let's get started. Let's go inside our src directory and create a package ROS2 pkg create build type ament underscore cmake. So this is a C++, so it has to depend upon ament underscore cmake. The name of the package, let's keep it cpp files. Right, let's keep it cpp files, and it depends on dependencies rcl cpp rcl cpp. Okay, now there are other dependencies too, but we will go to the cmake list and we will add it manually. Right now this is totally fine. Yes, we have successfully created our the package. Now let's build the package. Done. Now we can go to our VS Code and we could see that there is a package called as cpp file, and here inside the src we are going to create a new file called as MoveIt underscore interfaces random.cpp interface.random. Let's keep random join.cpp. So first step, we are including some headers. So we have a memory header, we have got some RCL CPP header, as well as MoveIt, MoveGroupInterface, Chrono, FStream, FileStream, many others. So let's include that headers. So here the memory header provides us smart pointers like std shared pointers used for managing nodes. Then we have got RCL CPP header. This is a core ROS2 C++ client library, not the server library. This is a client library used for creating nodes, logging, spinning most of the tasks. Then we have got something called as MoveGroupInterface file, which provides MoveGroup class for planning robots motion planning and execute using MoveIt2. Alright, then we have got some other like chrono as well as thread, which are used for measuring time and managing execution threads. And fstream and ffiles are something that I got it from internet. Let's be honest, I just went for Gemini, typed in few things that whatever that's required for me for in order to store some values inside the log. So it suggested me fstream as well as filestream, which worked really well for my case. So fstream is for writing logs or data to files, whereas file system is used to create directories or manage files. Then we have got ament underscore index cpp get package shared directory.hpp, lets you locate a ROS2 package shared directory path at runtime. So enough of this, let's get started. Now we will create a class called as simple MoveIt interface, and let's create some public variables or public methods, I would say. Yeah, it is suggesting me following things, but let's create a function called as move robot, that takes in our node, which we are accessing the node using shade pointer. So when I say shade pointer here, we can understand that the shade pointer, no. So we are accessing the node using shade pointer. Now inside the curly brackets, let's initially do a setup underscore move underscore group, the name of my move group. Now inside move it planning interface, which we have already uh, have those header files here. So planning interface, and inside that we do have something called as move group interface, and inside we're gonna provide node comma r, the name of our planning group. So we are interested in arm planning group, so we want to keep that same. Then you could always change it back to gripper, and you could do the same algorithm for gripper too. Hmm? now now we can access this move group object. Now we can set the planner ID to RRT connect. My bad. RRT connect. Now let's set our set the timing planning time. Let's keep it 5 seconds. That's usually good, 5 seconds. Now once again from the MoveIt planning interface, let's create MoveGroupInterface plan my underscore plan. So we are creating an object called as my underscore plan, whether so that we can plan our sequence of joints, and it checks whether our plan was successful or was it not successful. So after this, let's create a logger. Keep it searching for a valid collision free plan dot. There you go. Then HDD file system. Let's create a directory called as package underscore path, which I have not yet defined. It would throw an error as in what this package underscore path mean. So let's create a private variable. Now inside that private variable, let's create a std string which has that package underscore path. In my case, it's inside home administrator ROS2. What is the package name here? ROS2 tutorial. Yep. Then src. Let's create cpp files. Inside that, let's create a folder called as stream data. So every logger comes there. Every logging comes there. Now, after creation of this package path, we are creating a directory. Yeah, of course, that's done. Once we have created directory, we are using a log file underscore dot open functions from fstream. So these things would also throw an error telling that you have not defined what is log underscore file underscore fstream means. So let's define that once again, off stream. Yeah, let's open this package underscore path plus. Now let's keep that name as planning underscore time dot txt std ios out. So this would tell that we are searching for a text file called as planning time, and we are if it is not there, you create it. That's what it tells here. Now let's go for second step, that is loop until a valid path is found for 50 iterations, right? That's the whole idea. So while rclcpp okay, and counter underscore lesser than 50. Now it would throw once again an error that telling that what does counter underscore mean, right? So we have to define that too. So now to define that, unsigned int counter underscore 0. But before all this, I would I would like to say that we have to define a few declarations for chrono. So using declaration, these are global declarations that I am doing. So instead of using std chrono high resolutions every time, I can just use a duration cost or high resolution clock or milliseconds, which is quite simpler rather than writing this whole statement again and again, right? So that's the whole idea. Now loop until counter reaches 50. Generate a valid path. Generate a valid uh, joints. So how do we do that? The one good thing about MoveIt is that they have a lot of functions to do a lot of things. For example, we can get random joint values from move group dot get random function, random joint values. Now once we have this random joint values, we can check whether the random values that we have got is out of bound or is it within the robot joint limits. So how do we do that? Let's create a bool variable called as arm within bounds, and let's create arm underscore move underscore group dot set joint value target random joint values, random joint values. So we're gonna set this joint value uh, to the random joint values that we have got it from get random joint values. Then we'll check whether with this is within the bounds or it is out of the bounds. How do we check? It's simple if statement. We'll check within within bounds. So rclcpp underscore one. Yep. Tell give a warning that we are not able to get or generate. Yeah, we can tell the generated target is out of bounds, so we have to retry. Continue. So this would skip to the next loop iteration, right? Now after this, if it was successful, if the joints that has been generated from this function, that is get random joint values, were successful and within the bound arm joint bound, we can start the timer. We can start time by high resolution clock, and inside we have a function called as now we will auto plan a result arm move group.plan my underscore plan auto end high resolution underscore clock now. Now if plan underscore result, let's say if it was successful, let's use core functionality of the MoveIt to get whether the error code was success. If it was success, then we will once again log a comment onto a terminal telling that found a valid collision free plan, right? Yep, I hope that this is understandable. It's not that too confusing. So initially we call this move arm group, right? So move arm group is something that we're gonna generate this variable move arm group from the move group interface, planning interface node arm, which takes the parameter node as well as arm. Now once we generate this move group planning interface, then we set the ID to RRT connect, set the plan time to 5 seconds. Then we create a directory, then we open a file. After opening the file, we go inside a loop until we find a valid path. If it is not found, we iterate until it reaches 50 iterations. Once it reaches 50 iterations, it comes out of the loop and prints out the final comes out of the loop and shuts down the planning interface, right? Now, once we inside the loop, we have to generate a random joint. We set that random joint and we check whether it is within the arm bounds. If it is not, it would skip this loop and go to the next loop, right? But before that, we are going to generate if it is successful, we are going to start a clock and we are going to end the clock, and in between we are going to plan a planning sequence, right? So if the planning becomes even successful, then we can calculate milliseconds, that is duration underscore cast milliseconds end minus start dot count. So we get in milliseconds, that's important. Now we will move the robot arm. So till now we were only able to plan from start to goal, but we have not yet moved the robot. So we will move the robot right now. So how do we move the robot? Arm move group dot, same thing, we're gonna do move here, then rclcpp underscore info. Once again we are going to log some informative message onto the terminal using OMPLs RRT connect, and took around it's a long format, so let's keep it long double milliseconds as planning time. Now static underscore cast, let's keep it long. Now we will increase, since the planning was successful, we'll increase the counter. If it was not, then we will not increase the counter, it would iterate to the same counter. Now let's say if log underscore file underscore dot is open, if it is open, that's true, it should be open because we are already opening it here in this line, so it should be open. So this is just a checking guard. For counter using OMPL's RRT connect, and the planning took millisecond, yeah, milliseconds, and done. Now we'll go for else statement. If it was not, then rclcpp underscore error, failed to open log file. This is the one. Now let's say if the planning was not successful, it was failed, this part of the code will not run. Let's keep a else statement. cpp warn, let's keep a warning telling that node get underscore logger finally done. Now we will create a main function that takes in following characters. Init auto node cpp node shade simple. Let's keep the node name as simple move it interface underscore node. It's the node name, so you can keep any name. Then we will use executors which we have already have a header file single thread. So this, let it be single threaded executor, and executor dot add underscore node. Let's add this node. Right now std thread dot detach. This is our class name. Let's keep it as I think there's something wrong with my class name. This, okay, that's right. smi dot move underscore robot. Now if everything works fine and if somebody gives control C or some interrupt, it should shut down. So this is our code. I hope that there are no errors in our code here. Hoping that everything works fine, but before that we have to make some few changes in the CMake list. For instance, this doesn't just depend upon RCL CPP, it has to depend upon RCL interfaces, right? After that it has to depend upon these MoveIt packages. So if you have installed MoveIt properly, these packages would be there. Otherwise you would get some, if you get some error, try to install these packages. Now we will add an executable called as MoveIt interface random join, which is inside same name. This is the rename. Copy this part, paste it here. Dot cpp. Now it depends upon the target. It depends upon certain dependencies. For instance, yeah, it depends upon MoveIt interface random joint RCL CPP std. It also depends upon std underscore msgs. Let's keep that. If later part of the code, if I want to do some manipulation, I would need this std underscore msgs. Then yeah, these are the things. Now we do have an install targets. No, just targets. Random joint destination lib project. There you go. Now coming to package.xml. So yeah, before I go to what these lines are doing, so we are adding an executable for our CPP file called as MoveIt random joint. So what happens when you run this script, you should be able to see this name as our script name. Then we are going to install these into our shared directory, which is our project name by default. Then we go inside our package.xml. Here also we are depending on these packages as well as MoveIt packages. Okay, now this is done. God. Now let's source our workspace as usual. Let's keep things ready. Oh yeah, that's mistake. Let's go inside ROS2 tutorial. Now let's do install.setup.bash. Okay, so you should see our Gazebo spawning the robot. Then we launch controllers. Now the Gazebo has active joints. Let's run rviz with MoveIt. So you should have this r with MoveIt. Okay, now you can run the script to the different configurations, and yeah, that's the whole thing. So every time the MoveIt finds some valid valid motion, then it would move the robot, and parallelly it would log out the messages like what was the time taken by the robot to do certain the motions from start to goal. So we can at the end we can look at the robot's joint configuration, right? Yeah. So at the end we can look at the robot's planning time. So don't worry about this. This is because we have given our robot group as our arm. So it is trying to reach every point from start to goal in a random fashion with a random joint configuration. So let me pause the video here, and we will come back later and we will see what was the time taken by the MoveIt OMPL planning to plan a trajectory from start to goal. So yep, this planning has been done and it's successfully done for 50 iterations. Now let's look at our yeah, stream data folder. As you can see, for the count one, for the first iteration, it took 19 milliseconds for the planning. Then as you can see that on average, it took somewhere around um, 25 to 30 milliseconds. So by this way, we can create a simple code using C++ with the MoveIt API, and we can generate some planning timing for our the planner. And I hope that this part of the code or this tutorial was helpful. If it was helpful, Let me know what else I should be making video on. See you next time.